Hi, I'm Chris Matta. I'm a principal solutions engineer with Confluent. I've worked for Confluent for about 5 years. I focus heavily on financial services. So JP Morgan and Chase are my customers. I've been helping teams build solutions around Kafka for the last couple of years. And today I wanted to talk about how stream processing works with Kafka. We're going to go through a very quick Kafka kind of primer, like one slide. And then we'll talk about Kafka Streams, and we'll also talk about this Confluent project called SQLDB. And then I'll show some really neat animations that sort of get into the internals of stream processing with Kafka. That should be applicable if you're using Kafka Streams, or if you're using KSQLDB, or even if you're just writing your stream processors with the default vanilla clients. So let's jump in. What is Kafka? So it came out of LinkedIn. Confluent, the company I work for, was founded by the original authors of the open source project. Jay Krebs is our CEO. He was the lead engineer on this. It's essentially a distributed commit log that stores your data in the order it's written, and it has pub sub semantics. So it's kind of a data store. It's kind of a messaging system. It's a lot of interesting things. Now, what you do as a client is you either publish to a topic or you subscribe to a topic, or you can do both. Stream processors that read from one topic and write to another are very common. Because it's distributed, so we partition topics up into partitions. We distribute them across a number of brokers that are organized and are highly scalable. An individual or multiple failures in the system actually don't interrupt the service. Kafka can support transactions across multiple partitions. So as a producer, you can actually start a transaction and produce millions and millions of records, and then either abort the transaction or commit it. If you have properly configured consumers on the other side of that, they will only see that data once the transaction's committed. If you never commit the transactions, those consumers will never see the transaction. So when you persist data to Kafka, you can actually persist it with very, very strong delivery guarantees. So because it's a distributed system, as a producer or as a writer, you can actually specify your write concern. In Kafka, we call them acknowledgements or ACKs. So you can say, send me an acknowledgement when you have one copy in memory, or send me an acknowledgement when all replicas have a copy in memory. And usually that's very, very fast, right? So Kafka has pretty great performance numbers. Usually we can handle millions and millions of messages per second in a modestly sized cluster. End to end, typically latencies are between single digit and tens of milliseconds for each kind of hop. And we've seen a lot of success in adoption of this technology across all verticals. So not only financial services, but retail, commercial, .coms, manufacturing, IoT. I mean, you name it, there's probably a use case for Kafka in there. Everything that we're talking about here is built around these things on the right. So you have a Kafka cluster at the center, and your apps read and write to the Kafka cluster. The writers are called producers, the readers are called consumers. Everything we talk about will be built on top of that kind of structure, very straightforward. Inside of the Connect project, there are two other sub-projects. So, inside of the Kafka project, you have a Kafka Connect and you have the Kafka Streams. Kafka itself is the umbrella project. It encompasses the brokers and it encompasses the service. It also includes the Connect API. So Connect is a framework and a runtime for writing data integrations to Kafka. Confluent, there on the left, the company I work for, has written over 100 of these connectors. I think we're even closing in on 200 connectors if you include our partners. I know Viraj just spoke about how he's using Debezium. Debezium is built on top of the Connect framework. It allows you to write a connector either as a source or a sink. So if a data source connector is being used, it means you're pulling from some upstream system and writing to Kafka. So there's Debezium as a source connector, JDBC, there's an MQ connector, things like that. Sync connectors read from Kafka and write to some system downstream. So there's S3 connectors, there's Neo4j, syncs, we've got JDBC, of course, can also be a sync, things like that. So Connect is, again, framework and runtime. So you can build your connector and then you can run it on the Connect framework. It allows you to run the service in a horizontally scalable way. Tasks are distributed amongst all of the workers, and if one fails, it gets picked up by another one. So your pipelines become highly available and durable. Another project inside of Kafka is Kafka Streams. It's an open source Java, Scala, JVM language API. So you can use this to do massively scalable stream processing, and it's built entirely on top of the producer and consumer that we spoke about. If you compare something like Kafka Streams to another kind of stream processing tool like Spark or Flink, those are special clusters that handle the collection of data, the distribution of that data amongst all of the processors, and then also the aggregation and writing out of data. Kafka Streams entirely reads from Kafka topics and writes to Kafka topics, and it relies on the Kafka API to give you the horizontal scalability, the durability, the error handling, all of that, because it's built into Kafka's API. So as a consumer in a consumer group, if I write a consumer in Kafka, it will subscribe to a topic, it will do some things, it will commit its offsets and get the next batch. I can take that consumer and I can launch multiple versions of it, or instances, sorry, of it, same version, multiple instances, and it will organize itself into a consumer group. That consumer group will take some of the partitions and give them out to all the consumers in the group. Any one consumer fails, the partitions are reassigned to a healthy consumer, processing continues. So it's a really important thing to understand, because the Kafka API gives us that horizontal scalability, that durability kind of for free, and we build on top of that. So Kafka itself is a distributed event streaming platform that includes Connect, includes Kafka Streams. It allows you to publish and subscribe to events. It kind of acts a little bit like a message queue because you have pub sub, but it stores the data. You could store the data in a Kafka topic for a minute, for an hour, for 7 years, for infinity, and it stores it in a very fault-tolerant way. So you can lose a broker, you can lose multiple brokers. As long as you have a copy of the data, Kafka can heal itself when you replace those brokers. And then subscribing to streams of events and then writing them back to Kafka allows you to process those streams. And we'll talk about stateful versus stateless processing. And it can happen in real time, right? So that end-to-end latency, single-digit milliseconds, tens of milliseconds, very common. So you can actually process data as it shows up. This is a helpful kind of model. If you've been writing any kind of bash scripts in your life, this should help you understand sort of a nice way to think about what I've been talking about. So getting data into the system can be thought about, and out of, can be thought of the Connect API. There are these redirects, right? So if we cat the contents of a text, you can then use little stream processors. So this is almost like a microservice that does one thing and one thing well. So grep being a little filter and translate being a mutator. And the pipes in Unix are very, very similar to Kafka topics and Kafka clusters. So this is a really useful kind of parallel. This is an interesting way to think about Kafka Streams and Connect and the whole Kafka ecosystem in something that's very familiar to us if we've been doing anything in this space for any time. Like I said, Kafka Streams is built on top of Kafka clients. So the Kafka producer and the consumer are the primitives, right? A consumer subscribes to a topic. You start like a while loop. It subscribes to a topic. It receives some messages. It does some work on those messages, commits the offset, gets the next batch, right? A producer can send streams of data to a cluster, receives an acknowledgement, sends the next batch. Very low level. Kafka Streams is built on top of Kafka producers and consumers, has a higher level DSL and a lower level processing API. But you do things like you subscribe to a topic and then you do, map keys or map values for each. You can do aggregations, you can do filters, you can do branches. And all of the underlying produce, consume, commits are kind of handled for you by the library. And then a higher level abstraction and a little more simple is KSQLDB. So KSQLDB is built with Kafka Streams. So Kafka Streams is built with the core clients. KSQLDB is built on top of Kafka, or built with Kafka Streams. And in KSQLDB, you don't write Java or Scala, you write SQL, and that SQL is compiled into an application and then runs against Kafka. And we'll dig into that a little bit. Everything I talk about today, I'm using KSQLDB sort of as the interface to talk about stream processing, but everything we do with KSQLDB is possible with Kafka Streams, right? And I think it's just easier to sort of kind of grasp it. So on the left, if we were to build some kind of count processor, right? We want to aggregate things based on a key. This is how you might write it with a core Kafka producer and consumer. There's a lot of types, specific polling. There's a state store that you have to take and create here. You have some attempts and retries built in. You have to catch exceptions. This is a little bit more manual. On the middle here, you create a stream builder from a Kafka topic called input stream. You tell it what the data is, right? It's both are strings, the keys and the values. We're going to group by the value, count it, send it to a stream called counts with these surveys, right? So we're going to have a string and a long on the output. Lot less code here than the left, but with KSQLDB, we have even less code. You literally do select X count star from the stream you're doing, but group by this and then emit the changes. So this is actually a lot simpler. Under the hood, KSQLDB is instantiating a state store. It's built in. Kafka Streams is doing a similar thing. Under the hood, we use RocksDB as our key value store. It's embedded in the stream processor. It can overflow onto the disk. It doesn't necessarily need to fit in memory, but it's really extensible. But in KSQLDB, you can notice you really don't have to think about that, right? So we're using the state store to store the counts. As new things come in, we're counting it up and aggregating and going on from there. So this on the right is a persistent and permanent query. So this isn't not like a JDBC style, go get an answer and then get it back to me. This is something that will run and is designed to run basically forever. Think about it as like a query for the future, right? So we want to read all of these Kafka topics, and every single time a new record comes in, we want to count it, and this will run forever. KSQLDB, similar to Kafka Streams, is a Java app. So when you compile a Kafka Streams app, it gives you a jar, and you can package that any way you want. You can take your Kafka Streams app and create a Docker image and deploy it on any kind of Kubernetes or container service. KSQLDB comes as a container. You can run it on Kubernetes. You can run it anywhere you want. The clustering is handled by Kafka's API, like I talked about earlier. Because it's built on Kafka Streams and Kafka's transactions, we support exactly once processing end to end. We use the event timestamp to figure it out, the time semantics. So if you do aggregations on a window, we're using the event time as the timestamp, and we're putting it in the specific bucket for the aggregation. And then you can actually, horizontally scale out your instances. If you run a single KSQLDB instance, you can put it in an auto scaling group. If you start to see it lagging on the Kafka topic, you can automatically scale it up. More instances will be deployed. And as long as you have enough partitions to distribute amongst the instances, you will get more throughput and more lower processing times. And I'll get to that a little deeper here. So let's do a couple of sample use cases. Again, everything you see here can be done with Kafka Streams. This is just an easier way for us to sort of describe it. So in this view, or in this query, we're creating a stream called clicks with city, right? Under the hood, that's actually going to be a Kafka topic, right? It's going to be called clicks with city. And we're going to do creating that topic as select everything in the C topic and the u.city field from the U topic from another topic called clickstream, we're calling C. We're joining it, left joining it with the user's topic on the user ID, right? So the output of this will be almost everything, or everything in the C in the clickstream plus the city from the user's topic. And that's a quick, very easy way to do enrichments, right? This is stateless stream processing. Well, it's stateful because it's doing a join, but in this case, it's just going to output an enriched stream to a new topic. And this is happening in real time. You can obviously extend this. You can join multiple topics if you need to. What's happening under the hood is that, and I'll get into this a little deeper, but both the user's topic and the clickstream topic have the same number of partitions, and the user ID on the clickstream topic and the ID in the user topic are essentially the same field, and we use them as the key. So in Kafka, if you use a key, we will use that key to determine which partition each record goes to. So if I have 4 partitions, and that won't change, right? If I keep pushing messages to the users and the clickstream, the records with the same ID will be on the same partition. It's a deterministic hashing algorithm we use. So if I launch a stream processor that subscribes to both the clickstream and the user's topic, I will always have the same, partition 0 and partition 0 will be on the same instance, and I can join them together. That's how we do the joins. So they have to be what's called co-partitioned, and you can make sure you do that ahead of time. And I think KSQLDB will do that for you by rekeying and ensuring that a topic is created with the same number of partitions. Here's a little more complicated one, but it's a little bit naive. If anyone on here has done, fraud detection, this is a very naive fraud detection, but it's an illustration. So we're going to create a new table, right? In this case, a table is also a Kafka topic, but we treat the stream of events like a change log, and we materialize the table in the stream processor. So we're going to call this table possible fraud, and we're going to select from an authorizations attempt stream, right? We're going to select the card number, and we're going to aggregate how many attempts we've seen in a tumbling window of 5 seconds, right? If we've seen more than 3 attempts in a 5-second window, we're going to take that record and put it into the possible fraud topic. It's very straightforward, it's very simple, but it shows the power of something like KSQLDB. Kafka Streams would let you do this as well. It's a little more code, it's a little more functional, but nonetheless, you'd be able to do that. So Kafka Streams and KSQLDB support tumbling windows, we support sliding windows. A tumbling window is essentially a fixed width window that updates on the boundary. Hopping or sliding windows is a fixed width window that updates on some smaller boundary. So you can have a hopping or sliding window that's a minute updating every 5 seconds or something. And then we also support session windows. And session windows are cool because a session window is defined by a period of inactivity for the key, right? So if we see Chris Matta clicking on our website and I stop for 15 minutes, I can say my session of 15 minutes, session window is 15 minutes. That will close the previous window and do the aggregation. If I show up again after 15 minutes, it'll open a new one, right? So session windows are pretty powerful. KSQL and Kafka Streams support them as well. And then we can do operational stuff, like if we wanted to count the number of errors in an application. Again, this is an aggregation using count. We have a number of other aggregations like sum, and we have a bunch of scalar functions. We also support user-defined functions and things like that. You can also do simple arithmetic in the stream. Oops. But in this case, we are counting the number of errors and grouping by the error code and giving a count to that. So if you can imagine, this could output to an error counts topic, and you have yet another KSQLDB query that's listening on that topic and then alerting or sending special messages to other interested parties. This would be very simple. You could actually extend this in any number of ways. I have customers that have built UDFs that also enrich and attach longitude and latitude to an IP address using the MaxMind database embedded in the stream processor. You can join to another table for enrichment on rules or what to do when. So this is a very simple, straightforward thing. But I hope you could imagine taking this to a real world use case. KSQL is also a really good sort of stream processing Swiss Army knife, right? So we can actually create derived streams from other ones and actually do a rekey very easily. We can do things like increase the number of partitions from one source topic to a destination topic and keep the key. There's ways of doing this is very simple. You can imagine that these are a little more complicated if you were to have to build them in Java. So KSQLDB is really good at materializing your stateful processing in a key value cache. So the table that I created earlier here called error counts, or here called possible fraud, is actually a materialized key value store. KSQLDB will also let you do what's called a pull query. So a push query is, I'm just going to listen to the output of this KSQL stream processor. A pull query is, give me the value for this key right now. It's like a database query right now. So give me the sum of, or give me the current account value for this account ID. And what it's doing is actually letting you query the key, the materialized cache for a key. And we also support ranges. We support a number of other non-key queries as well now. You can build a number of event-driven microservices. We can do event deduplication. Imagine deduplication on a window. We can do event reordering. Sessionization is automatic based on that window. We can do validation with that. What it's not really good for is these ad hoc queries, things that mean like, let's go scan through the entire set of streams. That's going to take some time. It's not going to be a real-time operation. It's not very batch. It doesn't currently support secondary indexes for random lookups. There are things that we're doing in Kafka Streams right now that will eventually bubble their way up to KSQLDB to support secondary indexes and other OLAP style things, but it's not currently great for that right now, right? So if you think about the collection as two different types, right? I talked about streams. A stream is an immutable append-only sequence of events, and it should be reused to represent a historical series of events. That's a Kafka topic that we all know. We can take that and turn it into a mutable collection of events that reflects the current state of the world. And under the hood in Kafka, we're using a cleanup policy called compactions built into Kafka. A cleanup policy in Kafka determines how you delete data. A stream has a cleanup policy based on delete, which means delete any data that's older than some timestamp, right? So by default, if you create a Kafka topic, it'll be 7 days. You can change that to, like I said earlier, a couple of seconds, a couple of minutes. You can turn it off by setting it to -1 and hold on to data forever, as long as your brokers don't fill up. With compaction, you can compact a topic and say, keep the latest value for any key. And if we get a new value for that key, we're going to delete any old value for that key. And if you think about that, that can be used as a change log, and we can play the entire compacted topic and get a stateful table, right? And we use that idea in Kafka Streams, and we use that idea in KSQLDB to build these state holding objects that you can then query, or you can listen to the change events, right? Of course, I talked about Kafka Connect. So if you start to connect any of these systems, you can feed those events into Kafka, then you can write stream processors on top of them. And from here, I wanted to jump into more of an illustrated kind of internals really quickly. I know I've only about 4 minutes, right? Maybe, actually I have 4 minutes, a little more.
Yeah, a little bit more.
All right, time check there. Okay, so I wanted to kind of touch back on, if you were to build a stream processing system, you have to have connectors going from databases. You're capturing first-party events from applications. You're writing a stream processor. You're then making that connector materialize the thing out to a database, and then you're querying that database with an app, right? But KSQLDB can actually collapse all of this and make it look like its own kind of Postgres-style database, because KSQLDB can actually run connectors. It can actually, or integrate with an existing Connect cluster. It can do the stream processing we talked about and have materialized views. And it supports both pull queries, which are what's the value for the key, and push queries, meaning I'm just going to listen to this endpoint, right? Let's talk about both. I'll talk about stateless and stateful operations really quick. So if we create a stream of readings, we have a topic here in the middle with 3 partitions. and it's going to be value formative JSON. Let's pretend we're inserting rows here. This is actually real KSQL. You can actually insert rows if you need to. And we have our readings in here. We can actually highlight them and see what the data looks like. And then if we wanted to transform these, we're doing uppercase the location field. As they fly through here, this single instance of the stream processor will now have everything uppercase. You see that? Muffler, lowercase, muffler, uppercase, right? We can do filters. So if we play this, we can get data coming in. We'll do the uppercase, and then over here, we can then put a predicate on. So we're pulling data out of the readings topic, putting them into a clean topic, reading them out of the clean topic, and then only filtering for the higher than 41 records. So if you see over here, we'll get things. This is a reading 43, that one's 43, etc. So this is an illustration of how that works. We can then take both of those operations and put them together in a single instance, right? So in this case, we're going to uppercase the location, and we're also going to add this predicate of 41. And now one processor is doing this instead of two. Right? It makes it really simple. We can also process things with multiple consumers, right? So we're going to do the uppercase. We're going to also put it above 41. Now we also do a rekey, we call it. So we're actually taking the location and using it as the key over here and putting it into a topic called by location. We're also deriving a new stream called reading, and we're rekeying here. The keyword being partition by. And the partition by means take this field and make it the key for the new downstream. And you'll see that we have all, let's see, we'll see that all of these, let me pause this, hold on, get rid of that. This is a little bit buggy. There we go. We'll see that all of these, this one's going here. Its key is muffler. This one's key is wheel. So muffler's going down here. I'll hit play. You can see it. It'll land over here. So rekeying is very common in Kafka. It's very simple. You use the partition by on that. Let's talk about stateful operations really quick. A stateful operation requires us to hold on to a state store represented here in the middle by this little table. In this case, we're going to take an average on the reading of a sensor, and we'll hit play. You'll see that these readings will go in. We'll have a change log under the hood, and this change log is now materialized. And as things change, as new records come by, the sensor's averages are updated in real time. This would actually support a pull query. So I could say, select star from where sensor equals sensor 1, and I'd get the average back for that. Under the hood, I talked about this automatic repartitioning. So if we needed to group by area, Kafka Streams and KSQLDB will actually create a repartition topic underneath. You'll notice here that the key here is sensor 1, but now the key is the engine, or the key is sensor 3 in this case. Over here, we'll do the aggregation based on the area and then outputting that. So we're doing a rekey kind of automatically. You don't have to think about that. And then if you wanted to replay from a change log to build state, that's very simple. Create a table called part average, select it here, group by, and then this will output everything to a topic, right? Again, you can replay from a compacted topic and get that similar kind of output, right? We'll jump one more time, and then we'll talk quickly about streaming joins. I talked about it very briefly. We don't need to go all the way into that, but given two topics with the same number of partitions, we can actually join things together and enrich them. So we're joining brands on the sensors, right? And we can get the brand name out. And now we have new records with the proper brand name. We support inner and outer. I don't have to get too far into this. I don't think we have a ton of time on that. And then I just want one more and talk about scaling and fault tolerance built into Kafka. If I have a single processor here, of course, that processor will have to read from all of the partitions and do the things it needs to do. Of course, it's going to take its time because it's kind of working on the individual partitions as it needs to. If we launch multiple instances, like 2, now the partitions are actually given over to both. Half go to A, half go to B. Now you're processing twice as fast. And we can scale this to as many partitions as we want. So if we can have up to 8 processors because we have 8 source partitions. And that, of course, makes it much faster. Fault tolerance comes in when you have a failure, right? Or statefulness. So we can scale this out for state, right? So if we have 4 instances, you can see that some share of the source partitions exists in each of the processors. So A is responsible for sensor 1 and 2, B is responsible for sensor 3 and 4, right? If A fails, partitions for sensor 1 and 2 will actually be given to B, C, or D, and the state will be rebuilt because there's underlying state store, right? You can avoid the reprocessing penalty of a failure. KSQL and Kafka Streams support these standby state stores. This hasn't been illustrated yet in this tool yet, but you can imagine that B could have a state store of A in the background, and if A fails, B takes it over instantly. So Kafka Streams and KSQLDB support live standby state stores for instant recovery. And then quickly with high availability. So we have A and B, right? They're going into another processor over here. If, let's see, I think this wasn't written by me. This was my colleague, Michael Dragalis, wrote this. I'm trying to figure out what he was trying to do here. I haven't seen this one. And I'm going to give up on this one. It's a little too, I think he was in the middle of a project on this one. I have to come up with this one because it doesn't illustrate what happens when there's a failure, what I just talked about. But anyway, I hope this was illustrative and helpful. It's sometimes a hard concept to get your head around. So these little animations have been helpful to a number of people. So. Cool.
Okay. Thanks, Chris. I think there are 2 questions. One question is, the first one is the state store part of Kafka, or is that independent object that a developer needs to create?
That's a really good question. The state store is backed by a Kafka topic, the compacted topic that I spoke about, but it is actually materialized in the stream processor using RocksDB. RocksDB can fit in memory. If it doesn't fit in memory, it will spill the disk. When you create a KSQLDB instance or a Kafka Streams instance, you specify your state store directory that will create these memory mapped RocksDB files in.
Yeah, okay, that's good. The next question is, in the left join, is there a time duration?
So it depends on what you're doing. Left joining to a table, a stream to a table is not, there's not a time duration. If you're joining 2 streams together, you actually have to specify a within kind of piece of it. So if you go to KSQLDB or the Kafka Streams programming guide, it will talk about the types of joins that are supported and what you need to do. If you were to do a stream-to-stream join without a window, you would have these ever-expanding state stores that would fill up the machine. You have to give it some kind of window. So if I've seen a record for in the A topic, within 5 minutes of seeing it with the B topic, then the join will happen, right?
Yeah.
So there are rules around it because, you know, without rules, it would be chaos.
Yeah, I think the next next question is mainly about those animations. People like those and they're asking what tools.
Yeah, those were all hand coded by Michael Dragalis. I don't know if anybody knows Michael. He was like a big deal in the Clojure community a couple years ago before he started working for Confluent. He is a unbelievably brilliant engineer. He's a product manager, product owner for Kafka Streams and KSQLDB at Confluent. He just had a baby like 4 days ago. So I won't bother him about how he built them, but when he gets back.
An IPO and the baby at the same time?
His due date was, I think his baby came on our IPO day. It was a pretty intense day for him.
Congrats.
Yeah, I was texting him. I obviously haven't heard back yet because he's very busy.
Okay.
Great.